Looking at the new chapter, we're on chapter 2, section 1, and we're going to focus on derivatives during this chapter. So day 1, you can kind of see here what the objective of the day is. Let's find the slope of the tangent line, the slope of the tangent line to a curve at a point, and then we'll use the limit definition to find the derivative. So bumping ahead here. Oh, maybe we should go back here. What we're looking for is if I pick some point along the curve, I could draw in the tangent line to that point by using kind of a symmetric balance here where it's certain distance away from the curve on either side. I should also see that this tangent line is just skimming by the curve at that particular point. Well, don't you wonder what the slope is of that line? Well, that's what we're going to tackle this chapter. And you may say, well, that seems easy enough. Well, it is easy if I have 2 points. For instance, if I would attach a point here and maybe this point, I could calculate the slope of the blue line there. That's what we're going to refer to as an average rate of change. And what I'm after is a instantaneous rate of change at a single point. So in earlier math courses, you've been real familiar with working the slope of through 2 lines or 2 points. And we're going to change that up and try to do it through just 1 point. So derivatives are all about change, really more like a rate of change. And they show how fast something is changing at any particular point. The derivative gives us the slope of the curve at a point. And the derivative could also be referred to as a difference quotient. And we could think of that as being f of x plus some little value h minus f of x. So these would be y values like a y2 minus a y1 over x plus h, the x value, minus x for my input of f of x. And then we can see how this would be x plus h minus x, which would eventually just come down to h. So this would simplify out. And I would get this difference quotient. And we're going to be working a lot with this difference quotient. So the slope of a secant line can be calculated using 2 points. And the slope of the secant line is also referred to often as the average rate of change. If I had these 2 points, I could identify one of the points by putting in x. I get out f of x. So this point right here we could refer to as x, f of x. And you can see here, here's my x, and then travel over to the y-axis, and we get f of x. My second point I've identified as q up here, and I can refer to it as f of x plus, instead of delta x, let's just call that change of x h. And then on the bottom here, where that input value occurred, I could say that this is my x point of x plus h. Instead of delta x, we're going to refer to it just as some change of h. It too has an output, and that output would be a height of f of x plus h, giving us an ordered pair here of x plus h and f of x plus h. And if I let this value of h go really small, I would come up with this difference quotient that we were just talking about on the previous page. I would let this value here of h getting extremely small. Well, what would that look like on my picture? Well, that's saying then that this x plus h is traveling in closer and closer so that the gap between x and x plus h, that h is going to 0, or they're getting super close. Well, as you can see then, everything shifts downwards on this particular curve, and my Q is getting closer and closer to P, so that the secant line becomes a really good approximation to the tangent line. And that's how we're going to define a derivative, as the slope of the tangent line, and it's done through this difference quotient. Whoops, bumped ahead too far. All right, so the derivative gives us the slope of the curve at a point. So that's the word derivative. And the definition of a derivative, the derivative of a function is f prime of x defined by, and I've got one way of defining it, we just talked about it, this difference quotient, the limit as h goes to 0 of f of x plus h minus f of x all over h, provided that limit exists, of course. If it did not exist, we might suspect we have a vertical tangent line there, because vertical lines are undefined. Another way I could look at this, I could get a more direct answer if I knew the point at which I wanted to estimate my slope. I could do f prime of a, where a is equal to some number, some x value that we name. So the slope of the tangent line at some point x equals a. And this is what we would kind of refer to as an alternate definition of a derivative given at a given point x equals a. If f prime of x exists, we say that it's differentiable, or f has a derivative at x. So let's just go through a problem here. You know, we could sketch out the graph of this particular function. Well, looking at the function, I see x is raised to the first power. That means I have a linear function. And let's just go ahead and plot that. We have a -2 for our y-intercept, a slope of 3. So that's going to be an up 3 over 1. And I pick up this linear function, f of x equals 3x minus 2. This is a rather easy example to start with, but I just want to get you familiar with working out the algebra involved. So this asks us to find the slope when x is -3. So if I were thinking about -3 here, travel down, what is the slope at that particular point? Well, we can calculate it out using this definition of a derivative provided by the limit as x moves to a. Now in this case, this tells me right here that my a value is -3. So as x moves to -3, I want to evaluate f of x minus f of a. Well, f of x is simply 3x minus 2. I'm picking that up right here from the givens. And then I minus f of -3. And that means then that I'm plugging in -3 everywhere I see x. This is divided by x minus a, or x minus -3, keeping in mind our a value was -3. All right, we have everything set up. Now it's just a matter of simplifying out our limit and trying to come up with its solution. So 3x minus 2, I get minus, inside I have -9 minus 2 is a -11. And all over x plus 3. This minus will go to a plus. Simplify one more step, the limit as x goes to -3 of 3x plus 9 over x plus 3. I have it nice and simplified, so I'm going to stop for a moment and see if I can evaluate my limit at this stage. And that would mean I'm going to be trying to plug in -3 for my x, and immediately I notice I have some problems. I do get -3 times 3 plus 9 gives me 0. I get 0 over 0 on that. So that means I probably have a little bit of work to do. And obviously here we could factor out a 3, so I get 3 times x minus 3, and, oops, I'm sorry, that's a plus 3. X plus 3 will divide into x plus 3 one time, and my final solution here is 3, so f prime of negative 3 equals 3, which means the derivative of f of x at x equals negative 3 is 3. The derivative, getting that off of this notation, f prime, of f of x at x equals negative 3 is 3. And so I suspected it was 3 because it's a linear function and the slope is constant in this case. It's always negative 3 on that entire line. But it's a nice simple example to see how the math is going to play out. Find the slope of the tangent line to the graph of the function at the given point. We give the function, which is quadratic, and we want to evaluate it at x equals 2. So in this case, I want to let a equal 2 and evaluate it. So f prime of 2, this is just like we did on the previous example. The limit as x goes to a, but my a value is 2, of f of x, which is x squared plus 4x minus 1. Then I go into the minus f of a, so minus f of a, plugging in 2 everywhere I see an x, divided by x minus a, but my a is 2. I get that. If you want to note, this was f of x minus, and this grouping was f of a, which really was replaced with a 2, so it was really f of 2. Now, let's simplify algebraically. On top, I'm going to have x squared plus 4x minus 1. Inside my parentheses, I have a 4 plus an 8 minus 1 all over x minus 2. This looks like 12 minus 1 is 11. So one more line, the limit, and you want to keep writing your word limit over because that's what we're trying to perform here. I get x squared plus 4x minus 12 on top over x minus 2. Once again, let's try to plug 2 in for our x's. And I get on top 4 plus 8 is 12 minus 12. That gives me 0. On bottom, I get 0. That's not helpful, but it does tell me I should be able to get a solution. And I can do that if I try to factor this. So let's factor out the numerator, hoping that we get a factor that cancels with our problem factor in the denominator. And I get x plus 6, x minus 2 for a factoring. That'll give me that positive 4 in the middle. And this is interesting. This is a good sign. We get the x minus 2 to cancel. And now we can plug in, try it again, to evaluate the limit. The limit as x goes to 2 of x plus 6 is simply 8. So f prime of 2 turns out to be 8. What does that look like when we go over to the graph? At 2, if I travel up to 8, 1, 2, 3, 4, 5, 6, 7, 8, should be like right here. I have a tangent line that skims by there, and f prime of 2 equals 8. It tells me the slope of that tangent line is 8. The slope of the tangent line at x equals 2 is 8. So up 8 over 1 type idea. Finding the derivative of a function is called differentiating. There are several ways symbolically that we can show an expression is equal to a derivative, and that would be using the prime symbol, which we've been focusing on, and it's read as f prime of x. Another very common one that we'll use often is dy dx. These will be our two most common ways of referring to a derivative with the notation. This one would be the derivative of f of x with respect to x. Y prime is how I would say this. This is another one that will be very common, that we will use often. This one, not so often. Still, it's just the derivative of some function y with respect to x. So don't be surprised when you see these notations being used. On homework, the first type of problem you're going to encounter is estimating the slope of the tangent lines at a point. Actually, on each of these graphs, there's two different points. They showed point 1 by x sub 1, y sub 1, and then here I'd call this maybe point 2. If you can look closely, you'll see that there is a blue line highlighted on this. It'll be a little bit more obvious probably in your textbook, but I'll just highlight it there with that black line. Now, what I want to do is basically find the slope of this line. And you can do that by traveling across this line, trying to find some decent intersection points. I like this one because it intersects on the grid line. Do you see that? And that means that it'll be a little bit easier counting. This, as I travel upwards here, I notice that also falls on a nice grid line there. So I'm going to use those 2 points. And we know all about slope. So estimate the slope of the tangent line. I'm going to say f prime of x sub 1 is approximately, we're going to say delta y over delta x here, trying to get a slope estimate. So I'm going to have to travel up 2 units and over 3 to get my slope. So it looks like a positive 2/3 slope for this particular point number 1. For point number 2, I'll erase some of this work here, and let's go on and I'll travel over this slope line so you can see it a little more clearly on the video. Looking for those nice grid lines. This looks like a nice intersection on the grid line there. And the other one, where is another like intersection? Probably like right here. So drawing in my triangle, this gives me my change of y position. This is my change of x. Change of y is up 2. Change of x is over 1, 2, 3, 4, 5 units. So I would say f prime of 2 is approximately a change of 2 over a change of 5. And so that's what you're asked to do in homework on those 2 problems when you get there. Here is the homework being assigned for day 1, page 103, and it's 1 through 6, 6 through 8, and number 26. All right, good luck.